Welcome to the Space Telescope Public Lecture Series. Tonight's talk, The Art and Science of Webb Imagery by Alyssa Pagan and Joseph DePasquale. I am your host, Dr. Frank Summers of the Office of Public Outreach at the Space Telescope Science Institute. And I want to thank our wonderful tech team, Thomas Marufu and Grant Justice, who bring you this webcast every month. I will also remind you that the Space Telescope Public Lecture Series will continue to be online only throughout 2023. Our upcoming talks on February 7th, Supermassive Black Holes in the Centers of Galaxies by Darshan Kakad of the Space Telescope Science Institute. In March, a talk on active galaxies by Travis Fisher, also of the Space Telescope Science Institute. And in April, Understanding Planetary Habitability Using Exoplanet Atmospheres, seeing the atmospheres of planets to understand how are they possibly habitable. That's Catherine Bennett, also of the Space Telescope Science Institute. And if you want information about those talks, you can go to our website, www.stsci.edu/public-lectures. There you will find this webpage. On the lower left, you can see the links to our webcast, the current webcast that's going on now. Also, the archive of our webcast, both on YouTube and on the Space Telescope Science Institute pages. On the lower right, we have our email list, and you can sign up for the monthly announcements of the lectures and when the lectures are fully posted on YouTube afterwards. Also on that webpage are the lists of the upcoming lectures. And if you click on one of those lectures, you will find the description, as well as after it has been recorded, links to the STSCI webcast, as well as the webcast on YouTube. For the email announcements, as I said, sign up on our website. The alternative, you can subscribe to our YouTube channel, youtube.com/Hubble Space Telescope, all one word. You'll get the new video notices as well as the reminders of live events such as this. Finally, if you have comments or questions, you can send them to the email address publiclecture@stsci.edu. Our social media, we do social media for the Hubble Space Telescope, for the Webb Space Telescope, and for the Space Telescope Science Institute. We're on Facebook, Twitter, YouTube, and Instagram at those handles. I, as your host, am doing a tiny amount on Facebook and Twitter as Dr. Frank Summers. And now the news from the universe for January 2023. I'm only going to do one story tonight because I know you want to hear all about those Webb images, but it's an awfully fun story. And the story title I gave it is Peekaboo Looks into the Early Universe. So this is an image from the Hubble Space Telescope, and this image appears to feature this star, TYC 7215-199-1. That's a very long name, but it's actually just a catalog name from the TICO star catalog, which is a catalog of about 2.5 million of the brightest stars in the sky. But this image really isn't about the star. It's really about this small galaxy behind the star. This dwarf galaxy also has a convoluted catalog name. It's called High-Pass J1131-31. All right. And this is a galaxy that has just sort of appeared over the last 100 years, because that star is what we call a high proper motion star. It's moving relatively fast across the sky. As the sun moves in the galaxy and this star moves in the galaxy, it shifts position across the sky. And 100 years ago, it was directly in front of this small galaxy. So we would have had trouble watching it. So since this galaxy has sort of appeared from behind this star, people have gotten to calling it the Peekaboo Galaxy. Peekaboo, you're seeing a small galaxy. And this is a small small galaxy, okay? You talk about men as they're being giants among giants, right? This is really a dwarf among dwarfs, okay? Its size is about 1% the size of the Milky Way galaxy. So here is a comparison. On the left is the tiny Peekaboo dwarf galaxy, and on the right is a drawing of our Milky Way galaxy. And honestly, the Peekaboo galaxy is even smaller than this. I just wanted to make sure it was large enough you could see it on the slide. It's really small. It's only about 1,200 light years across. And so if it's 1% the size of the Milky Way in linear distance, it's 1/millionth the size in volume. So it contains at most 1/millionth the number of stars in the Milky Way galaxy. So when you stare at it, you can see, it looks kind of like a star cluster, right? It's a very small thing. I mean, the Milky Way probably has star clusters. It does have star clusters bigger than this entire galaxy. So being this dwarf among dwarfs, what makes it special? Well, Hubble can study the individual stars in this galaxy. It's about 22 million light years away, and we can resolve individual stars, and we can study them to figure out the abundances of elements inside this, okay? And that's what makes it special, the elemental abundances. Now, let me just remind you of, here is the chemist's periodic table of the elements, okay? And you see on the left, you've got the alkali metals, and on the right, you've got the noble gases, and you've got the halogens, you've got the metals and the transition metals. It's really, really complicated, okay? I mean, some people probably had nightmares about this from their high school chemistry class. But we're astronomers. We have a much simpler periodic table, and it looks like this. To astronomers, there is hydrogen and helium, which were created during Big Bang nucleosynthesis. So those were created at the beginning of the universe. And then there's everything else, which we lump into this category called metals, all right? And this is stuff that's made later. And because those metals are made later, the amount of metals in a star indicates how much the material that makes up that star has been processed, because you create these metals via, star deaths, the stellar explosions, supernova, planetary nebula winds, neutron star collisions, all sorts of things that process the elements to create these heavier elements, these metals, okay? So this is what makes the Peekaboo dwarf galaxy special. When Hubble examined the elements in it, it found it had very, very few metals, okay? This is what they call an extreme metal poor galaxy. For somehow, after 13.8 billion years of the universe, the material in this tiny galaxy has not been processed very much. It's only had, just a little bit of processing to create a tiny amount of metals. So this galaxy has stars in it that resemble stars in the early galaxies in the early universe, just shortly after the Big Bang, when there'd only been a little bit of stellar processing to create metals. So by studying this galaxy, which we can see because it's nearby, only 22 million light years away, we can use it as a proxy for studying galaxies in the early universe. So this Peekaboo galaxy not just gives us an insight into dwarf galaxies, it also gives us a look into what galaxies were like in the early universe. Our featured speakers tonight are my colleagues, Alyssa Pagan and Joseph DePasquale. And I'm so glad they came on here to give this talk. Actually, I had to bribe them because, they've been doing so many talks these days. They're like, oh, another talk, Frank? No, but I guilted them into it, okay? Alyssa came to us in October of 2019, and actually she joined just like 4 months before we all were sent home for the pandemic. So a good amount of her early time, she was working from home without the benefits of actually being in the office. She's back in the office now, though, and she got her dual degrees. She got a degree from Towson University in art and design, And then she went back for another bachelor's degree in astronomy at the University of Maryland. So she's got the art degree and she's got the science degree. How perfect for the job she's doing. And then she worked at the University of Maryland as a TA for a little while she says she repeatedly applied at Space Telescope until we finally accepted her. And we were very lucky to have her. Joe, on the other hand, grew up in Philadelphia. He did his undergraduate degree at Villanova in astronomy and astrophysics with a minor in physics, or was it a second degree in physics or a minor?
Sorry, it was a minor.
It was a minor in physics.
Yeah,
okay.
yeah.
But, like I got a minor in mathematics when I did my degree in physics. And it was like I took one extra course to do it. So you probably didn't have to take too much extra to get a minor in physics here.
Exactly. Yep.
Yeah. And then Joe went up to the Harvard-Smithsonian Center for Astrophysics up in Boston. And he spent 8 years working as a data processor, okay, doing the actual work with all the data for the scientists that were working there. And then he switched to public outreach and became an image processor for the Chandra X-ray Observatory, and I assume other missions that they run out of there. He did a fantastic of a job up at Chandra that we stole him away, and we pulled him here back in 2017. So he's been with us for like almost 6 years now. All right. And so this is our dynamic duo of image processing. Some of you, if you were watching last week on the Today Show, saw them appear on the Today Show. They've been doing talks like this all over the place because the Webb images are so popular. So I guess after the Today Show, this is going to be trivial for you guys, right? All right. We're going to tag team it, and Alyssa is going to start. So, ladies and gentlemen, Alyssa Pagan.
Hi, everyone. Thank you so much, Frank, for that introduction, and thanks for joining us, everyone. Let me get my slides up here. All right. And can everyone see that? I didn't get it yet.
We're not seeing your presentation.
Of course. When it actually comes time to do it.
It works so well in practice.
Okay, let's do that again. Oh, I always do this thing where, you actually have to click on it. All right. Are we good now?
Nope.
What?
We're still seeing the Zoom screen. It says you're screen sharing, but we're seeing the web browser screen.
Oh, weird. What? It was working. It was.
I know it was working. We did. Okay, it was working 15 minutes ago.
Okay, let's try this one.
There you go. Now it's working. Okay. That's perfect.
All right. I'm just trying to build up, All
right. The anticipation. The anticipation is killing us. Go for it.
Anyways, thanks everyone. I am Alyssa Pagan, as Frank mentioned, and I work with Joe DePasquale, and we process the imagery for Webb. So we take astronomical data from Webb and Hubble and other observatories and create color imagery. And we do that to support our news releases, our outreach products, and other educational resources. So that's what we do. But before I jump too far into the process of how we do this, why do we even care about infrared light? Why do we study it? And why do we need a space telescope like Webb to look at infrared light? So you might be familiar with the electromagnetic spectrum. Of course, we're all familiar with visible light, and that's just a very specific part of the spectrum that we can see with our own eyes. But as you can see, it's a very, very tiny part of the spectrum. On the right, we have the shorter wavelengths, so the higher energy wavelengths, like the X-rays and the gamma rays. And on the left, we have the longer wavelengths, so the lower energy wavelengths, the radio, the microwaves. And so if we just studied what we saw, then we'd be missing all this stuff in understanding our universe and space. And in particular, infrared. And of course, it's not just about studying it, but we actually use light to transfer information. So if we didn't actually know about this, then we wouldn't be able to sort of text our friends or turn on the TV or, listen to the radio. So it's very important. And we'll focus on infrared, which is really important for understanding astronomy, objects in general. And so what exactly is infrared light? So we feel it as heat. And so you can kind of think of it, if you've ever seen the movie Predator, he has infrared vision. So he's looking for the prey, he's hunting them down, he can see them like in a bush. And so that's how it works. And so on the left, we have an image showing that. We got a fellow here, he's sticking his hand in this trash bag, which is opaque to us in visible light. We can't see the hand. But if we take an infrared camera, all of a sudden we can see that hand is emitting the heat and we can capture it. And so the brighter regions that are hotter are showing up in sort of this white yellow, and then the cooler regions are this bluer purpler color. So, and it works, that mechanism works the same when we're looking at space, because we can look using infrared light to see through dust and gas, whether that's to see sort of the stars that are hidden within the dust or to see behind the dust, to see sort of these young galaxies. And well, that goes into this part as well. Why infrared light is important is because it helps us to see farther into the past. And this is because of something called cosmological redshift. And all that means that space is expanding. And as space expands, light that's traveling through space also extends or stretches. So if something's emitting far away from us in visible light, by the time it gets to us, the wavelength has been stretched so much, redshifted, so that we see it in infrared light. Well, we can't see it, but that's why we need these telescopes to be able to see it. And that way we're seeing sort of the first galaxies and the first stars that have formed. So it's a very powerful tool. And the reason why it needs to be in space, of course, is because the atmosphere primarily absorbs all this infrared light. So we need it to be above the atmosphere so it doesn't interfere. And also we need it to be very cold because it is heat. So we don't want sort of extra signal coming from the heat of the instruments, which is why Webb has a sun shield, and it's why it's located where it is. And that's kind of to go full circle at the importance of being able to see in all these different wavelengths of light, just like we have Hubble that sees a little bit in the visible, well, a lot in the visible, a little bit in the infrared, a little bit into the UV. Webb sees farther into the infrared. And that's the same reason why we have medical equipment too that sees in different wavelengths to tell us different things about our body. For instance, we use X-rays to see our bones versus like MRIs to see our soft tissues using radio wavelengths. So it's all very important to our understanding. Another question that comes up often when people are looking at these images is, are they real? And then what goes along with this often is this how it would look like if we could actually go there? So the first question I can answer very easily and say it's 100% real in that it's real data. It's real astronomical data that is being collected by these telescopes. It's just light that we cannot see or measure with our own eyes. So would it look like there if we could go there? Well, not quite, because again, our eyes are not as sensitive as these telescopes. And of course, we cannot see in infrared, but it's a huge tool. And just because we wouldn't see it this way doesn't mean the universe doesn't exist that way. We're getting more information. And so a nice way to also sort of explore this a little bit further is to look at a parallel into a different science field, in this case, microbiology. And like astronomy, microbiology uses advanced instruments in order to help our understanding, to see things that we can't see with our own eyes. In the case of microbiology, we use microscopes. And then of course, for astronomy, we use telescopes. So on the left here, we have this black and white image of the coronavirus. This is how it appears through an electron microscope. And so we're getting information here, but it's not quite as interesting or evocative as sort of this image you see on the right. This is actually a rendering that was produced by the CDC. And we're actually using the color to sort of separate these different structures, the different proteins that are actually existing. And this is very similar to how astronomy works, in which we are using color to showcase different structures as well. But in the case of astronomy, these structures and colors aren't arbitrary. They actually have physical meaning. And we'll get into what the wavelengths mean and why we prescribe the colors that we do a little bit further on. But as you can see, when we're combining all these wavelengths together, we're getting that full color image. We're seeing all these different structures that are contrasted by the color, which are saying different things that are actually physically happening in this particular image. And then also, why do we make color images in the first place? Like, it's really fun and it's really nice to look at. But of course, I kind of mentioned it before, is that it's really important to be able to see the data, to visualize it. So numbers are great for data analysis and science and research, but just to get like a broad overview understanding, big picture understanding, it's helpful to see all the data sort of at once in a color image. And then of course, we want to illustrate the scientific discoveries and the concepts, because Science is for everyone. What we find out is something that we want to share, and we want it to be digestible. We don't want scientific literacy to limit sort of what people get from these discoveries. We want to make it, accessible. And that sort of ties into engaging the public. We want images that are compelling, that inspire, that make you want to get interested or involved in astronomy, and maybe inspire a next generation of engineers or image processors or, whatever. And so those are the goals that we have in mind when we're processing these images, and it affects sort of our decisions that we make as we go along. Okay, so now let's actually get to sort of a general idea of how we process Webb data. And so the start is something we call image stretching. So it might come as a surprise to you that these images don't start off in color. They actually start off in black and white. And so this is actually one image of the Webb deep field taken through one specific filter or one specific wavelength range of light, the 2.7 micron filter. But as you can see, it looks very dark. It doesn't look like there's anything there, but there is. It's just because these telescopes are so sensitive that we have to actually scale the brightness values in order to show them or display them on our screens. So you can see here, there's all this data here, but it's all kind of locked up in the black point. So this is a histogram, and this represents the brightness distribution, or the values here, or the pixel values distribution. And you can see that they're all kind of pushed to the black end, but we want to literally stretch this histogram out. We want to distribute it so that we can actually see the details that are hidden in the dark end. So a nice way to kind of look at this is like a simpler example, and we have this 4-value parrot here. We have dark gray, we have black, light gray, and white. And we have this distribution of these 4 pixel values here. Now, what if we wanted to scale the brightness values of this image, or stretch it, so to speak? So on the left here, our first example, we haven't done anything. This is just linear, 1-to-1, no transformation. Now on the middle part, we have scaled the brightness values, but now you can see that while we're trying to bring out this darker gray, we end up completely losing the brightest values. So we can't differentiate between these pixels, which is not good, because then we're losing information. And so what we end up doing, and this is the stretch that we want to do for astronomy, is we want to do what we call a nonlinear stretch. And that just means performing a transformation that helps to emphasize these darker regions, bringing out those details in sort of the parrot here, but we're not losing those values on the brightest end. And so we can see another example with this image of the Webb deep field. And this is what we call the linear stretch. This is something that we don't want to do, because as you can see, even though we're bringing out those faint structures in the background, we're completely saturating these regions. It's too bright. We've lost information here. And you can kind of see that here in this histogram because it's been cut off. It's been clipped. So that's information that we can't get back if we continue on. So that's why it's so important to apply what we call a nonlinear stretch. So we're preserving the highlights, we're bringing out these features. You can kind of think of it as bringing out those midtones, and we are stretching out this histogram across this range of values. So we get a really nice contrast-driven image. So let's look at that with an example of the Carina Nebula. So for the Carina Nebula, we have 6 different filters here, or 6 different specific wavelength ranges of light that we collected. And here they are non-stretched, so this is linear. We haven't done anything. This is straight from the telescope. But for all the filters, we have to do that stretching. We have to scale the brightness values. And so that's what we do here. You can see like it comes to life. All of a sudden you see all this detail and structure and information. And that's exactly what you want to do. Okay, and now we get to the second step after this, which is the chromatic color, or prescribing the color. So I kind of mentioned this already, that these images that we get start off in black and white. And the way we prescribe color is we collect specific wavelengths of light through this filter wheel. And so this is actually a video of the mid-infrared instrument, the MIRI instrument, which is collecting the light, redirecting it through this filter wheel. The filter wheel can move, and then we can get different specific wavelength ranges of light. And then it's redirected to the detector, so our camera, and then it gets sent back to us. Now, how do we prescribe color? So we see visible light as the shorter wavelengths being the bluer color and the longer wavelengths being the redder color. And so that's the relationship that exists with visible light. So we extend that relationship into the infrared, essentially. So even though we can't see an infrared, we can use that relationship and apply it to the infrared. So in essence, you're taking the infrared wavelengths and shifting it into a visible color space. So now your shortest wavelength in infrared is your bluer color, and etc. So you can see that's what we do. That's how we apply color in chromatic order, where our shortest wavelength filter here is prescribed blue and so on. So cyan, green, orange, red, and then yellow, which seems okay. We got an outlier here because, right, this should be red. But the reason why we do this, we're not actually breaking any conventions here. This little guy on the right is actually very, very hot hydrogen gas, and it's a very specific filter range. And it actually gets captured in another filter, this 2.12 micron filter. And so if we switch it out, we're not breaking any rules here. And the reason why it's important to actually designate this yellow rather than red is because it's a really important feature that's showing you where these really hot young stars are embedded in this dust. And if we just prescribe it red, we're losing all that information there. And that's the whole point, is we want to showcase the science and the astronomy and the, all this really cool information while making it compelling. Okay, so after we have performed the stretching and we're prescribing colors, we want to do one thing on each filter before we continue. And that's dealing with stuff with like artifacts. And artifacts are just intrinsic to the detector, the telescope itself and the calibration and all of it. So it's something that you wouldn't actually see if you were there. So things like readout noise from the electronics, or you have these sort of dark centers of stars, those are introduced by the calibration pipeline. So all this data gets cleaned up. And because these stars are saturated, they get replaced with null values, because it's just a warning to the scientists that you can't perform any sort of photometry, you can't perform any sort of analysis on this because it is no longer reliable. So that's just sort of, that's why that is there. But we have to remove those because, of course, we're not looking at the sky and seeing these black in the center of stars. And we also have these striations again, which is from the electronic readout noise. So we have to do things to remove this. And we have a lot of algorithms to do this, but this is just some of the things that we end up doing in sort of photo editing software, is removing those bands and replacing that area of the dark cores with the nearest neighbor. Okay, so this is our first initial color composite. After we've done the stretching and prescribed all the colors, this is what we initially get when we combine them additively together. And so there's no one point that it turns into a subjective from the objective. We're always sort of weighing the art and science elements as we go along and thinking of the story we're trying to tell, the science story we're trying to tell. This is sort of the first phase of that. Now, that being said, there still are artistic principles or aesthetic principles that we're thinking of all the time and that we're applying. And things like clarity, color, composition, things again that help tell the science story. In fact, there's decisions that we've already made that are aesthetic decisions. Things like I was talking about the artifacts that we remove, but there's actually an artifact in here that remains, and that's what we call the diffraction spikes. So this 8-spike star, we keep that in there. And why do we do that? Well, there's a little bit of a whimsicality there. It's sort of like the twinkling star is just sort of what you think of space. So when you think of a space image, you think of these twinkling stars. And so that's sort of the convention there. But also it acts as like a signature to Webb, because the diffraction spikes come from the light interacting with the hexagonal mirror of Webb, and also the 2 struts that are holding up the secondary mirror. So that's why you get these spikes. And so we keep them in there so like, oh, we're looking at Webb. Also, it'd be really hard to remove them. It would take a long time. We do have algorithms in place to sort of replace those areas with samples of data. But the better way to do that would actually be to rotate the telescope, get another exposure of it, and fill that data in over the diffraction spikes or where they overlap. But that costs a lot of money, and there's a lot of competition for Webb time. So it's not the most feasible thing to do. Also, a decision that we've already made that you might have not thought about, you've probably seen this image, Carina Nebula, and if you have, it's been primarily in this orientation. Even though the Norfolk Convention for astronomers is the orientation on the right. Now, why is that? So there's no true north-south. So it could be really anything. It's just a convention that astronomers use, but it was a choice to change the orientation. And that choice is important because the one on the right feels a little bit unbalanced, unstable. And also, if we crop this down, we're going to lose a lot of real estate. And of course, we want to showcase all the details in the data that we got because it took a lot of time to get it. So we're thinking about that. And we're also thinking about how does this provide context? So this helps us feel like this is a landscape. This feels more familiar, something we might have seen, something that we can draw a parallel to. So in the case of this Carina Nebula, these mountainous regions, they're being eroded by these hot stars. And that's similar to what we see, on Earth, where we're looking at mountain ranges that are being eroded by weathering or natural forces. So that parallel helps with the story and the understanding of what's actually happening in this image, besides just making it feel a little bit more stable, like more appropriately weighted, and helps your eye move across the image. Okay, so let's go back to our initial color composite. This is where we're kind of looking at this more as a photographer would. So we're thinking of sort of the white balancing. We're thinking about color balancing. So we use the center of the stars for our white references in this particular case. And normally we would neutralize the background, make sure that we have equal number of our red, green, and blue values, because that background should be very, very dark gray or almost black. But in the case of nebulae, we don't really have a region to use as that reference because there actually is some dust. So there is a little bit of, or I should say, there's some gas back here. So that's not true, dark sky. And so there is a little bit of by eye that we have to do, but it is a very iterative process, and it's one that we do with the scientists as well. So starting from this phase, I actually end up shifting this image a little bit closer to the blue part of the spectrum. Now, all the relationships between the colors remain the same. They're just slightly shifted to really bring out these two different processes at work here. We have the mountain range on the bottom, which is just the very dense dust. And then on top, we have the hot gas, and sort of that complementary nature of that orangey dune-like scene with the sky scene feels a little bit more familiar and also helps with that contrast. And of course, I want to bring out these features even more because that's, we got all of this data and these different filters that are showing us different things. We really want to bring out the contrast and the color separation here. Now, this, I went a little too far here, so I have to take it back. And that happens sometimes. You work on an image for a while, and then you get so, wrapped up in the pixels and bringing out all that detail that you kind of have to take a step back and be like, oh, that doesn't seem natural anymore. So you kind of have to take it back. And at this stage, again, I'm working with the scientists, and this region we have here is sort of this blue gas that's sort of coming through this mountainous region, and it seems to be overshadowing it, obscuring it. And this is very real. This exists. But speaking with the scientists, they felt like it took away from the 3D nature of the dust and the structure. So we want to go back in there and really enforce that dust 3D landscape. So that's what you can see here. It goes a little fast, but you can see that we get a little bit more of the structure back in here. And we've toned things down a little bit. And then in the end, this is what we are left with, the final image. And there's a lot of ways to sort of approach an object, and different objects will be processed differently. And they'll also be processed differently by different people. And so I'll let Joe get into that a little bit more in the next presentation.
Thanks, Alyssa. I'm going to pick up from here. So let me share my screen, get the slides going. Okay, so I am going to continue talking about the Carina Nebula image, but before I do, I just noticed that Alyssa was talking about the 8-pointed stars on Webb, and I thought we could explore a little bit about why they appear that way. It actually has to do with the optical system of the telescope. In a system like this, every hard edge imparts a diffraction pattern onto light sources, right? So a point source star is going to interact with the hard edges all along the mirrors. So all 18 hexagonal segments are going to contribute something to the final appearance of the star. In addition to that, we have these green lines representing the diffraction that's imparted by the support struts that hold up the secondary mirror. And so when everything comes to focus at the detector, you get this pattern, which we see in every bright star that Webb observes. So that is the origin, sort of, generally quickly summarizing where that comes from. That is the origin of Webb's unique diffractions pattern. Now, jumping back into the Carina Nebula, what I'd like to do is talk about the MIRI observations of this. Remember, Alyssa had discussed a little bit about the mid-infrared instrument. We took MIRI data of this same region. It's a smaller field of view, so it actually takes up this region here. But the origin of the appearance of this image is actually an interesting story. Let's see. Yes, it's the mid-infrared instrument. And remember, Alyssa had showed this movie. This is actually the final frame of that movie that just shows you there's, the pick-off mirror, then the detector at the bottom, and the filter wheel, which is where all the colors come from. So this is just to sort of ground you in what MIRI is and where that data is coming from. Now, MIRI is observing in the longer infrared wavelengths. And so if we were to combine the data together of NIRCam and MIRI, according to the chromatic principles that Alyssa has laid out, you would expect to see something like this, where the blues and the teals and maybe the greens would be confined to the NIRCam regime of the image. And then as you move into longer wavelengths of the MIRI, we would have yellows, oranges, and reds. It turns out if you apply that process to the data, you get an image that looks more like this, which when I first put this together, I wondered how we were going to deal with this. It's not a very aesthetically pleasing image. The purple sky, the green clouds. It's interesting that astrophysically speaking, most of the stars in this image appear in the short wavelength infrared bands, and so they don't appear in the mid-infrared. And so you end up getting a lot of blue stars that are just pure blue, which looks very unnatural in the composite color image. So the next step for me, the next logical step was to say, well, okay, this looks kind of strange. What happens if we just make an image in the MIRI wavelengths alone? And what do we get from that? So shifting this just to MIRI and applying the chromatic ordering to the MIRI wavelengths, what do we see? We see this. And when I put this together, I thought, well, this is actually a really interesting image. It's very evocative. It's very different from what we saw with NIRCam. In fact, it actually reminded me of Monet's Rouen Cathedral series of paintings. Monet went to this area of France and painted the Rouen Cathedral over 30 times at different times of day, trying to capture the essence of the atmosphere, of the lighting, of the atmosphere, whether it was morning or evening or mid-afternoon, the effects of the environment on the scene itself. And you get 30 very different looking paintings, even though it's the same object. So if this image brought that to my mind as I was working on it. And so then I thought, well, okay, we have this beautiful image from MIRI. We also have this beautiful image from NIRCam. Is there a way that we can combine them together that emphasizes both the astronomy, the astrophysics of what's happening, but also emphasizes the beauty that each of these instruments provides in this scene? And so we came up with this idea of interleaving the short wavelengths, the middle wavelengths, and the long wavelengths of each camera together, right? So now we have what we call near MIRI cam, where the short wavelengths of NIRCam and MIRI are assigned blue, and then we go to green and to red. And that was how we came up with this final version of the image here, which, aesthetically speaking, we have stars with white cores in them, which looks more natural. But astrophysically speaking, it's still astrophysically relevant, right? The young stars, the stars that are embedded in dust, they still appear dusty and red because they show up red in both NIRCam and MIRI. And it actually gives us more information than either one of them alone. NIRCam gives us all of the stars in the background. MIRI gives us a deeper, we penetrate deeper into these clouds to be able to see these young stars in the process of forming with their jets shooting out in different directions. Okay, so that is the story of the near MIRI cam. And now I would like to shift focus to the Tarantula Nebula. This is one of my favorite images of the early release observations. This one was actually the first image, the first data to come down from the telescope. And of course, this is that image. And when this was released, it was actually compared to like old masters Renaissance era paintings, right? Like Caravaggio. So I did a little research and I found a painting that I thought kind of captures the quality and the essence of this. And that is Caravaggio's painting of Judith beheading Holofernes, which, despite its macabre nature, it's actually the colors here and the quality of the light really echoes what I think I see in the Tarantula Nebula. And just keep that painting in mind, it'll come back later. I do want to go all the way back to the source data though, and talk a little bit about where this came from and how we planned this observation and put it all together. So in both the cases of Carina and Tarantula, these are mosaics made up of many different images. In both cases, I believe it's 6 filters. So let's zoom in and look at the raw data that we get from the observatory. We're going to back out to the very first frame. Okay, this is when we take observations with Webb, it takes a series of exposures and it adds that together to get to the final image. So this is the first exposure. We call it a stage 0 image. So it's uncalibrated, and it's about 161 seconds of exposure time. So it's, like 2.5 minutes roughly that the observatory was just collecting photons of infrared light and creating this image. And you can see here that there's already some stars and they're saturated. And so this is actually the origins of the black holes in the centers of stars. If you have a saturated region in the very first exposure, there's no way you're going to be able to get valid information from that. So the pipeline processing will assign null values or zeros to those values, those pixels. And so you end up getting these black holes. But watch as I step through, for each exposure, one exposure on Webb is actually 8 individual of these 160-second exposures. And you can actually see the image sort of come into view with each additional exposure as I step through it. Now, this next one is going to be the next step in the calibration processing. And it's where you'll see the black holes come into play. So now we've gone from the 8 individual exposures to one calibrated image. This is called a rate image. It's actually not calibrated yet, but this is the combining all of those 8 exposures together to get the depth and the detail in a single exposure. But you can see if I bounce back and forth, where you have those bright regions now, that was saturated data, that's invalid data, so it's been assigned black. Now you fill in a lot of this through using dithers, which means you just sort of move the scene around a little bit and you take multiple exposures and you build up an image that fills in all of these holes. Moving on to the next step of the calibration pipeline, we see this slight change in the appearance of the image. This is just a distortion correction. And so what that means is that the detector is maybe slightly angled. And so the light is coming in, it's not coming in exactly parallel to the detector. And so to account for that, you have to apply this distortion correction to get the proper aspect ratio for the final image. And so this would be the stage 2 calibrated image from our pipeline processing. It has been flat fielded, so it's removed a lot of the instrumental artifacts. If I go all the way back here, you can see there's actually a lot of instrumental artifacts that are present here that can be completely subtracted out of the final image. And then we'll go back to the full field. So in this case, the Tarantula Nebula image is actually, for each filter, is a combination of over 40 individual exposures. And there were 6 filters. And so we're talking about combining together over 240 individual images to make this final mosaic image. And then this is just one filter. I think we're looking at like 3.3 microns here. The final image is actually made up of all 6 filters, and that's where we get the colors from, of course. So let's break that down and take a look at that. We're only looking at 4 of the filters here. So the shortest wavelength is the 0.9 micron, the longest is 4.4. We'll take the colors out. We're sort of working backwards from the way Alyssa had demonstrated this. And in particular, I just want to draw your attention to this F335M. That is a narrower band filter than the ones that have a W next to at the end of their name. The W stands for wideband. M in this case stands for medium band, and then you've seen N as well, N is for narrow band. And that just means a filter that allows less light through. And so for the 335M, we're talking about a filter that allows light of a specific frequency, 3.35 microns, and only a little bit of that around that area gets through to the detector. To get a really clean image in just that one specific wavelength, you can actually do something called continuum subtraction. And so in this case, we subtract the 200W image from the 335 to get the bottom image here, which gives you the light of a very specific kind of light. In this case, it's a warm dust, polycyclic aromatic hydrocarbons, or PAHs. Now, coming back to our painting here, we can sort of conceptualize this continuum subtraction in an interesting way, I think. Let's take this painting and break it down into its color channels, right? Red, green, and blue. That's how we perceive light, as Alyssa alluded to earlier with the eyeball. What if we were to take just the red filter of this image and look at that? Now, seeing the backgrounds, the tapestry in the background it shines brightly in the red filter because it is a red object. Skin tones are showing up here. So there, skin is very bright because it has a lot of red in it. So in a composite image, there'd be a lot of red. But imagine if you wanted to just be able to see the light of blood, right? So you could continuum subtract everything but the specific wavelength of blood from the image. That's kind of what we're doing with continuum subtraction. So going back to our color images, now, if we combine all of these together, we get this image as the final version. And this is, of course, not the final version. This is what I would consider, if you're a photographer, this would be like the raw file from a camera. And this needs to be color calibrated, white balance adjusted. We do adjustments to the tonality, to the contrast to get to the final version of the image. And rather than step through all of that, I will just allow it to fade from one to the next. And then we get to the final version of the image here after all of those steps have been applied. Shifting gears to the distant universe, I'd like to talk a little bit about our image of the deep field and how that was put together. So SMAX or SMAX 0723, this was Webb's first deep field image. We saw a galaxy, definitely at least one galaxy in here that's over 13 billion light years away. So this was a really monumental image, very impactful, maybe not as aesthetically pleasing as some of the other images from the first releases, but definitely an impactful image demonstrating Webb's capabilities to see all the way into the early universe to those galaxies that formed just a couple 100 million years after the Big Bang. So this image was pulled together through 6 different filters using the NIRCam instrument. So here's each one of those individual filters shown in black and white. As we see them, it's already been stretched, according to the principles that Alyssa described in her part of the talk. So we're looking at that here. NIRCam is very capable of looking at the universe in many different colors of infrared light. So it has a lot of filters and a lot of ways to slice infrared light. In the case of the deep field image, we used this arrangement of filters, these 6 filters here. So we have a really nice broad range of infrared capabilities from NIRCam here. Having 6 filters allows us to combine the data in such a way that we can assign the colors cleanly through red, green, and blue channels using 2 filters per channel. And it really is just a linear combination, right? So the blue channel is just the 2 shortest wavelength filters added together and divided by 2. So you get an equal weighting of both of those filters. There are other ways that you could slice and dice the data to create a color image, but to me, this seems like the most straightforward and clean representation of the data. So the green channel is then the definition it's defined as the next 2 longer wavelengths combined and divided by 2. The red is the longest wavelengths. So when we do that, we get this version of the image here. And this is, again, this is like the camera raw file. This needs to be color balance adjusted, white balance adjusted. And it's interesting when we're working with a deep field image, we have the opportunity to apply white balancing using the data itself. As Alyssa was saying, with the Carina image, we use the stars and the cores of stars as the white reference. For a deep field image, we can actually utilize the fact that we have plenty of galaxies in this image as our white reference. And so I have these 2 boxes here. The top long rectangular box, that defines the background region. And so that should be a region that's sort of relatively free of any part of the image, any kind of galaxy or star. We want that to be the reference for a neutral background. And so we're trying to subtract off, any excess light in any one of the filters so that we can get sort of a neutral gray as our background value. The other box you see here on the right, that is indicative of the type of galaxy that we would use as a white reference. It's a face-on spiral galaxy. And the reason that works so well as a white reference is because spiral galaxies contain all the populations of stars, from the youngest to oldest, representing all the possible colors of stars. So from blues all the way to reds. So it works really well as a white reference to use the entirety of a spiral galaxy as your white reference. When you do that, sort of everything else kind of falls into place and the colors appear more natural here. So looking at this now, I can see the background galaxies are taking on a much more red appearance, which is what we want to see. We know those distant galaxies should be showing up in the red channels because they are red shifted. The foreground galaxy cluster has taken on sort of a more white appearance as opposed to the greenish hues that we saw previously. And so the color balance here was a very important step. The other issue that we dealt with the deep field image in particular was variations in the background through each filter. And so that sort of manifests itself here as a blue box in the bottom right. And that blue box is just there because, again, this is like a mosaic. So we're combining multiple images together. And it just so happened that in some of those images, the background levels were a little higher than others. And so when you've combined them all together, you get sort of an excess of blue in one part of the image versus another. And that has to be subtracted out. That can be handled in pipeline processing before we start working with the data. But at the time we were working with the deep field data, this was soon after launch. The calibration had not been completely finished yet. And so we were working with data that was based on ground-based calibration. And of course, the observatory had been launched. It was in space. It was in a new environment. And we had to understand that calibration a little better before we could move forward. But we had to take these observations and get them out there. So we sort of had to calibrate by hand on the fly as we were going. And in the case of the deep field, it was actually a large amount of that was done sort of by eye. Here, I've isolated just the short wavelengths channel. So this is the combination of the 0.9 and the 1.5 micron data. And I used what we call curves adjustments to balance those pixel values in the boxes and try to get a uniform background throughout the image. And so now this next slide should be an animation that shows stepping through each one of those curves adjustments. And as they're moving, you can see that the overall background is sort of unified. We're getting a much cleaner image, and the background is becoming much more clear. In the end, we have a really clean image. We have to be really careful though, because the foreground galaxy cluster here actually has the glow of very faint stars that have been sort of flung all out from around it. And that is it's a very faint signal. And so it could easily be sort of crushed in this process where, this ring of material here from these stars and this area down here, that could have easily been crushed. So I just had to keep that in mind as I was adjusting the background levels for the final version of the image. So after applying this change, we get to this version of the image. This is a little bit more uniform in its background. And at this point, there were some artifacts that had to be dealt with, cleaned up to get to the final version of the image, which we see here. And the final adjustments were some of the artifacts, cleaning up some artifacts and also getting that background down, suppressed down just a little bit to give you sort of that sense of the deep space background from which all of these galaxies are sort of popping out. And and then what I like to do with this image is actually we can compare it to some previous observations. So we'll zoom out a little bit here, and we will reference this against previous Hubble observations of the same region. Now, this is slightly unfair of a comparison because this was only 2 hours of exposure versus Webb's 12 hours. But still, it gives you a sense of the difference of what Webb and Hubble have here in looking at this version of the universe. Being able to pull out some of those really faint galaxies, only Webb can do that. Hubble is not going to be able to see the really, really distant or the really dusty galaxies, things that have been redshifted so far that they're sort of outside the range of what Hubble can see. This is the Hubble infrared image. Remember, Alyssa mentioned earlier that Hubble is capable of seeing infrared. It sees a little bit into the infrared. And so this is that view of this region of space in infrared from Hubble. And then this is the view from the previous flagship infrared observatory, the Spitzer Space Telescope. It had a much smaller mirror than Webb's, and so its resolution capabilities were much more limited. But it was able to detect, the signals of these galaxies in infrared wavelengths, similar to what Webb can see. But I really like doing this slow fade from the Spitzer to the Webb image, and you can see as the universe comes into focus here. So finally, I thought I would just like to ponder a little bit of the question of why do we do this, right? Why? I mean, Alyssa already talked a little bit about why do we study infrared light? Why do we use Webb? Why do we need Webb? But also, why do we put all this effort into creating these color images? And what is the significance of that? Now, personally, I think that these images, they speak to an innate curiosity within us to understand our place in the universe, to understand where we come from and what we're made of and where we're going. And it really is true when you think of as Frank was mentioning earlier, to bring this full circle, he mentioned the astronomer's periodic table, where hydrogen and helium and everything else is metals, right? And that comes from the fact that in the Big Bang, the materials that were created, or all of the material of the universe was created in the Big Bang, but only hydrogen and helium had enough time after the Big Bang and the universe cooled. We only had enough time for hydrogen and helium to form. All of the heavier elements had to form later on, millions of years later, after the first generations of stars formed and died and exploded and populated their environments with heavier elements. And so quite literally, we are star stuff, to quote Carl Sagan. We are made from the materials that were generated in those generations of stars. And we are the universe attempting to understand itself. And so, as opposed to give in to despair, when you look at an image like this and you ponder the enormity of the universe, there is a tendency I've seen, at least online, to give into despair and to think like, oh, we're so insignificant. We have no place in this universe. We're such a tiny speck. But really, these images, they give us a window into our origins. We're looking at the raw materials that make up solar systems and planets and ultimately life. And so I feel a deep sense of connection to other people through pondering the universe, through looking at these images. And I think that's an essential part of what makes them important and why we do this. To take that even further, physicist Alan Lightman provides some really good context to why it's important to observe the universe. How do we fit into that, right? In two different ways. One is, if you think about the human brain, it's made up of neurons, and there are approximately 100,000 billion neurons per human brain, right? And it just happens to be almost the same amount of stars that make up a galaxy. And so as you're walking around and you see people in the street, you can think of them as each being their own little galaxy, right? You're a galaxy among galaxies in the world. And so that provides a certain perspective, right? The other one is scale sizes. If we think about scale sizes and how do we compare to the enormity of the universe, well, if you took the average human and you were to divide them in half multiple times, how long would it take, or how many divisions would it take to get to the size of an atom? It turns out that's about 33 divisions. And then going in the other direction, if you were to double the size of the average human, how long would it take, or how many doublings would it take to get to the size of, say, a star? And it happens to be about 30. And so in terms of thinking of things in scale sizes of doublings, we exist in a scale size that is roughly halfway between the fundamental particles that make up the universe and stars, the fundamental particles that make up galaxies. And so it does put it into perspective, the importance of understanding our place in the universe and why we're here and where we're going. And with that, I will say thank you for your time, and we would love to answer any questions you may have.
All right. Thank you, Joe, and thank you, Alyssa. We had a lot of great comments online on the chat and YouTube. They loved you, especially the professional photographers out there that were learning all your secrets, and they're now going to make their images just as cool as the Webb Telescope images. Well, all right, they have to have the source material first, but so I want to start with a question about Hubble versus Webb. And Joe, you did a good job of showing that they show different things, especially those background galaxies that Webb sees so much better than Hubble. But I wanted to know if there are different image processing techniques or a different mindset you use, because YouTube process Hubble one day and then Webb the next day and everything. So are there different different techniques or thoughts you use, or really just does the same techniques apply to all of the astronomical data you deal with?
That's a good question.
Yeah.
Are you looking at me?
Yeah, I'm looking at you, Alyssa.
Okay. Yeah, no, so I would say the overall process is like very similar. Like I feel like the mindset is very similar. I think with Webb, at least for the early release images, since the reference files and the calibration files, it just took a while to get used to dealing with that and those sort of artifacts, that takes a little bit more time to kind of get it set up. While with Hubble's pipeline, it's so refined after all these years that the data is just so clean that you kind of can just jump right into it. So I think that with Webb, it's just the setup takes a little bit longer. And I would say that's like the biggest difference. And then like, as Joe said, like you really want to bring out the faintest things, because like that could be a galaxy that no one's ever seen before. So you concentrate on really and you do this with all astronomy images, but particularly with Webb, we're really concentrating on sort of gaining the best signal, but suppressing the noise, but really bringing out those faint details that, are the early universe. So that's kind of what we keep in mind, I think.
Joe, do you have anything you want to add to that?
Yeah, I was just going to say, building on what Alyssa said, the process is remarkably similar, processing Webb data versus Hubble. We're using that same approach of applying color chromatically. It's just that with Webb, we're working in infrared, but it's the same process. It's just, applying color according to wavelength. And there are subtle differences between the two. Of course, the diffraction patterns of stars in Hubble versus Webb are very different. And of course, the instrumental artifacts that we have to deal with between the two observatories are different. And so we have to address them differently, but otherwise it is very similar.
Okay, great. All right. So the other question that I can't help but asking, being the astronomer on the visualization team, working so close with you guys, is that I truly appreciate that you guys have astronomy degrees in your background, as well as being these image processors. And Alyssa, you have your art and design degree as well. And you mentioned a lot in your discussion how you go back and forth with the scientists, okay? So could you just, elaborate a little bit more on this combination of art and science? And to me, that's sort of the crucial point that people don't get, that it's not just all science and it's not just all art. It really is that collaboration. So Joe, you want to start us off here on this one?
Sure, yeah. So again, not to beat a dead horse here, but chromatic ordering is so important and it's scientifically driven. The reason why we apply color the way we do is because of the science. And everything that we do when we're processing these images is with respect to the original source data. We're not trying to introduce things that weren't there, and we're not trying to take things away that are there, with the exception of the instrumental artifacts, things that we know are imparted because of the optical system of whatever telescope we're working with. So it requires the knowledge of the objects that you're looking at, to have a good idea of what this should generally look like, right? So as a starting point, when you pull that color image together, knowing kind of generally what the final image should look like really helps. And so having that background in astronomy informs the decisions we make as image processors to get to that point. And I'll let Alyssa pick it up.
Alyssa, you mentioned things about knowing that this is dust and this is, the ionizing gas or et cetera in the stars. And so how important is it to have that astronomical knowledge as you're doing the image processing?
It definitely helps just to have that sort of intuition, because you have a little bit of insight there while you're processing the image. And then, it's a little bit easier for Hubble imagery in the sense of those symbols that we've developed or connections we've developed, like with galaxies. We know that those, really bright blue stars, that represents these young stars, and that's why they're blue. And then of course, if we're looking at sort of the dust, they're kind of like this reddy dusty areas, and the spiral arms are sort of the cooler dust. And those are sort of things that you're looking out for, just little keys that you want to make sure is reinforcing the story. Because if you start showing things that don't reinforce the story, it gets confusing. So you want to build off of what we've already developed, sort of this legend that's sort of been built in astronomy conventions. But again, doing it in a way that's interesting and exciting. So, but yeah, it's definitely, it's a combination.
Yeah. And you're going to develop a close personal relationship with polycyclic aromatic hydrocarbons over the next few years, right?
Oh my God. Joe is right. I could never say that. Never say that, right?
We love dust.
All right. So Grant Justice is going to join us here. He's been following the chat on YouTube and picking out questions out of YouTube. So Grant, why don't you turn on your video and give us some questions from the chat? Uh-oh.
Absolutely.
There we are. Okay.
So the first one, there are two questions that are very similar. And I kind of want to highlight them both. So
ask one of one and one of the other.
Yeah. They're very similar. So why do processors use different tones when processing images, not the graphical colors of the filters? This person says when they use the graphical tones specified in the graph of the telescope filters, they get different than what they see.
Okay, so yeah, I'll jump in, and I think with the the question is referring to the actual color of the filter, right? So, and
Yes.
this would be applicable to Hubble data because Hubble is a visible telescope. With Webb, it's infrared, right? So it's beyond any color that we can see. But certainly for Hubble, in general, if we're doing like a wideband color image, we might use red, green, and blue filters, and those would be colored red, green, and blue. It's when we get into doing narrowband or combinations of narrowband with broadband where the choice of colors is important, and being able to have the flexibility to slide those colors around within the visible spectrum, because you may only have, 3 filters that are sort of centered around red. And so if you color them all red, you're going to get a very red image, and it's not going to look very good. So if you take the shortest wavelength and give it blue, and then green and red, you'll get a more aesthetically pleasing, but also a more scientifically informative image.
Yeah. Have you guys done many narrowband filters from Webb where you've had to do the specific color choices, Alyssa?
Not quite. Like I didn't keep it perfect in relationship to the spectrum, I suppose, in that there's we maintain sort of the spacing exactly. It really is what Joe suggested. Even though we're using narrowband, it's really a way to get a color balanced image, which is very difficult with narrowband, again, because we're not capturing the full, sort of covering the full spectrum. And also it's just about separating the colors enough so we can actually differentiate the different structures and processes. And like Joe mentioned, if you have 2 filters, 2 narrowband filters that are very close together, sort of on the longer wavelength and they're both red, then you're losing information rather than gaining information. So you want a little bit more separation. So maybe they're both on the redder end, but you make one orange and one red so you can actually get the information that those filters are giving you.
Right. And I will say, as an astronomer, it's important when you look at these color images to be able to differentiate between the 2 filters, because that's what you're trying to do to gain the insight in terms of, oh, well, the silicon filter is seeing this, and then the oxygen filter is seeing this, and you'll be able to then guide your analysis of this.
Yeah, this is directly related to the origins of the Hubble pellet. Any astrophotographers out there will know the Hubble pellet. It's because of this.
So that actually leads us perfectly into the next question, which is from Niels. I mean, first off, everyone loves the images, but you already knew that. That's why you're here. What is it that it actually tells you when you are looking at those images? Like, we're bringing it all the way back. I know you've already done a talk on this. I would highly suggest looking up Joe's other talk that he's done with us, by the way. But bringing it back as to like why we're doing this in the first place. What is it that it shows you when you separate it out, when you combine it into this?
So Grant, are you asking the RGB images, what people get out of the RGB images?
Yes, yes. Okay. The RGB images along with a little bit of the spectroscopy involved.
Alyssa?
So yeah, this depends really on the object that we're looking at, right? So which gets a little bit confusing. We apply chromatic order, so that relationship remains the same, but what it's telling you is different. So like, for instance, with the deep field, as Joe mentioned, the redder galaxies are further away, or they're more dusty. But in general, the smaller, redder galaxies are further away. And things that are nearest to you, like are more white, more blue, more yellow. And so you're actually differentiating things. The color is actually showing you distances. But if you're looking at something closer to us, like the Carina Nebula, that's showing you more of sort of the temperature of these gases and their composition, where they're located. So you're differentiating things like if you have, if you're looking through the dust, and you see like a really red star, that's like it's a cooler star because it's embedded within this dust region. So these cues are kind of different depending on the image you're looking at. But again, that chromatic ordering is separating like temperature, processes, or distances, or even more if you're looking at sort of spectra and beyond.
Yeah, it's giving you an insight into the astrophysics that drives the appearance of the image that you're looking at. So, Grant, behind you, you have 30 Doradus, the Tarantula Nebula, and you've got, on the left side of you, or at least the way I see it, you've got the NIRCam image, right? And on the right side, you've got NIRCam and MIRI, so mid-infrared wavelengths of the same region, right? So that's actually showing you something really interesting. You're seeing the same, like that cluster of young stars that's really bright
get out of the
blue
way.
on the left, sorry, which is now blocked by Grant's chair. That cluster of stars almost completely disappears in the mid-infrared. It's gone, right? Those stars, just like we saw with Carina, the stars, they show up in near cam and then they're gone in MIRI, in mid-infrared wavelengths. There's astrophysics there. There's a reason for that. And the colors tell us something about that.
Yeah. And let me just say that from an astronomer's point of view, these RGB images are not the ones that they're going to do the science with, okay?
Right.
But they can help guide the science by pulling out features that astronomer goes, hey, and then he goes back to the black and white images and processes those through his analysis software to pull out the information he's looking for. So the science is always done with the high dynamic range black and white images. But it doesn't mean astronomers are human. You give them a nice color image, they start to see more in it. And the Joe's comment about how stars appear in the near infrared but don't appear in the mid infrared was one of the interesting things that we thought about before we got those first images, right? Because we chatted about it in our group discussions that like, wait a minute, we're just the stars, in Spitzer only appeared in the blue channels, right? And so it adds a whole new dimension to processing these images.
Absolutely. I actually like this next question. Have you seen any JWST images that have been processed by someone else? And if so, what did you think about them? I love this.
Oh, this is a booby trap question.
It is.
I'll keep it simple. No, it definitely yes. And it's very exciting. It's so cool to see the response from people about Webb. The fact that it's showing you that people can access the data, like anyone can access the data. It can be a little bit hard to navigate sort of this archive, but if you go to mass.stsci.edu, you can go grab all the data that's been taken from Hubble and Webb. There might be a proprietary period where you have to wait 6 months, but max a year, but most of the data is already available. And it's nice to see what people think of, because again, like I mentioned before, not everyone's going to see the image the same way. And when we're processing an image, Joe and I are very much guided by the science discovery. So we're kind of following the lead of the scientist, while someone else who is processing the data might see something else that they find interesting that they want to show. And so having that different lens and that perspective is really cool, and it's fun to see. We might be a little jealous that you got to process it, but that's about it.
Yeah, I find it hugely inspiring to see how inspired people are by Webb, and they have a desire to go in and understand more fundamentally how it works and get the data and work with that data and make their own versions of the images. That's great, and I wholly encourage it.
And this is a seriously change from when we were doing Hubble image only a decade or so ago, right? People didn't go into MAST and regularly process them. And now everyone got really excited about Webb, and we got a lot of groundswell of people doing this. So this is really, really good for getting astronomy out there.
Yeah.
And Joe, that leads us to, would you say something about NASA's Astrophoto Challenge?
I was just going
project
to say
you're involved in. Thank you.
Yes. So if you are interested in working with real data from NASA observatories, we've made it somewhat easier to get to the data through a program called NASA's Astrophoto Challenge. And what that is, if you Google Astrophoto Challenge or NASA's Astrophoto Challenge, you have the opportunity to work with real data from Hubble and Webb and Spitzer and Chandra and something called the Micro Observatory, which is ground-based observatories. And you can take that data and make your own images from the real data and submit them to be analyzed or viewed by professional astronomers. It's a great program we've been running for years on different objects. The one that's currently running is looking at the Pillars of Creation image that was recently released. Well, for the Webb image that was recently released, but there's data from Hubble, Webb, Spitzer, and Chandra, I believe, in that challenge.
Yeah. And that challenge runs through February 28th, if I remember correctly.
That's right. Yeah.
Okay. So get to it, and you can process you can do your own interpretation of some NASA data.
Right.
All right.
Without having to go through the archive.
All right, Grant, after that plug, let's get back to the questions. Grant, you're muted, or I couldn't hear you.
Yeah.
Yep, that was my bad. Shameless plugs are always welcome. All right, so are the single image processes applied differently when animations / zooms are created? This is probably more for Frank.
Well, no, it's not actually, because when we need a zoom into an image, the visualization that's more the 3D work. But Alyssa is our master of the zooms to get into these images. You want to talk a little bit about that?
Ooh, I'm learning things.
Yes. So I'm trying to remember the first part of that question, which I think was like creating the animation like between frames. Is that the question? Like I'm not sure if I understood the first part.
The question was, are the single image processes applied differently when animations or zooms are created?
Yes. So the overall process is the same in the sense that we still want to make like the best, most compelling image that we feel that we can make and bringing out the details, but we might adjust it sort of in the end. But usually what happens when we make a zoom image, so to speak, like if we're doing an image for Webb, and is we process the Webb image and then we get sort of these intermediate images like the ground-based telescopes. We use Fuji a lot, and then we go into sort of a more intermediate one in between Webb and DSS, for example. And we usually actually adjust those wider context fields because it's easier to adjust those than to sort of go in and adjust sort of these much smaller field of views where like that sort of stretch is very important to it. And like that was just like you worked very hard to get that stretch to bring out that detail. So you don't want to kind of like undo it, so to speak. So generally the process is overall the same in order to make sort of those seamless transitions between one or the other in terms of like color balance or tonality or contrast. So yeah, I would say like the other plates that we use to zoom in to the final image are the ones that we usually adjust. Hopefully that.
Okay. And that. Joe, could you elaborate further on that? So like when we create the 3D visualizations and we're flying into an image,
Right.
What sort of image processing is required there?
Yeah, so those visualizations, they're based on the actual image that we built from the data, right? So we take an image, say, last year we did Hickson Compact Group 40, HCG 40 for Hubble's anniversary, and then we did a 3D fly-through of that. And the 3D fly-through is built from the press release image. We actually go in, and the image processing that takes place is to actually extract the different parts of the image. So we'll pull the stars out, and then we'll pull the galaxies out and make them separate layers. So they're coming directly from the image itself, and then they're placed in 3D space. And then the only thing that you have to fill in the background, right? If you pull the galaxy out, we don't know what's behind the galaxy. So we sort of fill that in with sort of the average background level of sky. So then that gives you this depth perception as you're moving in towards it. You see the galaxy moving against the background. That's how we go through that process.
Right. And the process is even more complicated when it comes to nebulae, because you pull off the front layer of the nebulae. What's behind it? You got to fill in that stuff. And so like when we did Cosmic Reef, we had all sorts of fill in and such to work on those.
Yeah, but the good thing about it is that we, working at Space Telescope, we have access to plenty of astronomers who, it's their life's work is to work on these objects. And so we consult with them and make sure that the decisions that we're making, that the artistic decisions we're making as image processors or as visualizers make sense and could be, plausible, scientifically speaking.
Yep. All right. Grant, what else we got?
Is STSCI/NASA making attempts to process or present the data in some way that can be seen by visually impaired people? Like, are we doing accessibility for any of these images other than the alt text, which we're already doing? Chat, if you haven't seen the alt text for the Webb images, go see it. It's amazing.
Right. I mean,
yes.
that's obviously the first answer is about.
Yes.
Now, do either of you want to comment on the alt text?
I think it's great. Our writers, our writers have done an excellent job of taking alt text to a new level, right? Really describing everything you see in these images in such exquisite detail.
Because usually the alt text just says image of Carina Nebula.
Right, exactly.
And they've taken it and they've turned it into a visual description of the image. And so the thing I have in my head about what alt text is this isn't it. This is a pure visual description. Now we have other projects that we work with for the 3D printing of like they did of Stefan's quintet.
Right.
You want to talk about that?
Yes. So we have like sort of almost like a relief map that's built up from the MIRI image of Stefan's quintet. And what that is, it's like a table, like a physical table, where you have the image sort of represented on the table, and then the brightness levels of the image corresponds to depth of bumpiness, right? So you can sort of move your hand across the image and feel where there may be a bright star. There's going to be like a big bump on the table. Additionally to that, there are audio snips that actually correspond to different parts of the image. So you can, move your hand across something, and then you'll interact with a button, and that button tells you something about that specific part of the image. So this is, an attempt to reach out to a broader audience and engage people, blind and low vision people.
Right. And I will just mention that in addition to that, a project that's based at Space Telescope, NASA's Universe of Learning, has an accessible learning resources project that's based out of up in Boston at the Center for Astrophysics, where Joe used to be. And they will also do visual descriptions. They will also do 3D printing things, as well as sonification. They'll run a line across an image and have the pixels translated into sound. So there's a variety of those things. Okay. Another question, Grant? Alyssa, everything okay with your internet connection?
Not sure.
Well, maybe that's a good note for us to end on then.
Okay, you got one more question, Grant, or?
No, they've done a great job answering all of the chat so
Okay,
far.
let me just check. I think I've gotten through all of those things. Yeah. Oh, actually, somebody asked something about angstroms.
Oh, okay.
Which was really just a unit thing. Alyssa, you want to explain what an angstrom is?
It's just another way to describe a wavelength. So like nanometers is like 10 to the 9th, we'll say, or that's like how I remember it in my brain. And then like angstrom is it's -10. So it's just like a helpful way to use it for science. I honestly, this is like back from my astronomy days, so I'm probably not to talk about it. But like, for instance, like to describe wavelengths for Webb, we use microns because it just makes the most sense, because that's just the easiest way to show that number. But it really just depends on what wavelength or what sort of part of the electromagnetic spectrum you're working on and what makes sense to use. So yeah, it's just a different unit. Make sure you pay attention to those.
Yeah. It's an astronomy specific unit. Yeah, it's an astronomy specific unit.
Right.
And it's more for X-ray astronomy, right, Joe?
Angstroms?
It's you get down to a few angstroms, you're X-rays, aren't you?
Yeah, true. Yeah. I mean, I usually think of it in electron volts, but yeah.
Yet another unit.
Yep.
Specific to that astronomers use all the time.
Yeah.
So we do have some interesting jargon in our field. How about that?
Yeah.
All righty. Thank you so much, Joe. Thank you so much, Alyssa. And thank you, of course, Grant. This has been a lot of fun. I'm sure we'll get, you guys will get a lot more requests to do these talks, because everyone's just so interested in the Webb images, and seeing how they are made just, turns on a light for so many people. All right, next month, February 7th, supermassive black holes in the center of galaxies. Please join us. We can't wait to see you then. Bye, everyone.